Jai Hind all. Myself Amita from Ajay Kumar Garg Engineering College, Ghaziabad. So here in this video lecture, we are going to discuss the topic operational amplifier, where the concepts are very important and all the complex problems can be solved by using this simple concept that can be applied to all the operational amplifier circuits. So here I will be telling you only one concept which is going to work with all the problems and with all the numerical problems of OPAMPs. So here we have taken the topic from BC 101. The subject code is BC 101 and the subject name is Electronics Engineering Fundamentals. Here we go. So this is my basic OPAMP circuit. As we can see in this particular diagram, it has two terminals. One is positive terminal, as we can see in this diagram, and one is negative terminal. The positive terminal is called as non-inverting terminal and the negative terminal is called as inverting terminal. Here is the output. So the output will decide whether whether this whatever we have given at the input, the output tells whether it will be inverted or non-inverted type of signal we are getting. So what is operational amplifier? Actually, this is very important to know that the input impedance of the operational amplifier is very high, whereas it is having very low output impedance. The input impedance is ranging from few megaohms and the output impedance is always in the range of 100 ohms. So OPAMP is having two inputs, as I said, and only one output. So here we have the basic OPAMP circuit. The OPAMP symbol which we use, that is, we have one this terminal, inverting terminal, and this is non-inverting terminal. Sometimes we apply some V plus and V minus also with the symbol, just to show that OPAMP is what? OPAMP is an IC, integrated circuit, and each integrated circuit or IC is working with some applied voltage, and this applied voltage is given as V plus and V minus at pin numbers 4 and 7. We will see later on. So here one terminal is inverting and one terminal is non-inverting, just to show this thing. Now this, since I told that 741 IC is known as the operational amplifier IC, in this diagram we can see the IC pin diagram here. See, this is my operational amplifier circuit. The inverting terminal pin number is 2, right? The inverting terminal pin number is 2. The non-inverting terminal is pin number 3 of this IC, and supply we are giving this at terminal number 4 and at terminal number 7, like this. So this is the DC supply which we are giving, that's plus V and minus V. This IC can be working only with this particular supply. Now from pin number 6 we are taking the output. It's as simple as that. 8 is not connected to anything and 1 and 5 are the offset nuts. Now here we have dual OPAMP circuit also. We are having some ICs with 2 OPAMPs. So we need not to worry about this for this particular subject, but just for information that we have 2 OPAMPs in a single IC chip. Okay, there are 2 OPAMPs. One OPAMP is this and second OPAMP is this. Somebody talks about this dual OPAMP, then you can say that yes, there are circuits which are having more than one OPAMP circuits. Here the operational amplifier. The operational amplifier, as here Vi input is applied at non-inverting terminal and output is being amplified. See, output is amplified and in phase with the signal, input signal. Whereas when we give supply to the inverting terminal, the output is amplified, of course, since we are passing it by the amplifier circuit. But see, here the signal is 180-degree phase shift, with 180-degree phase shift. Okay, the positive side has been converted to the negative and the negative part of the waveform has been converted to the positive. That means 180-degree phase shift we can see very clearly in this diagram. Here it is for the first 0 to 180-degree. We can see the waveform is upwards. Here we can see the waveform is downwards. So this is the total function of the inverted waveform which we are getting at the output number 6, output at pin number 6, 2 inverting terminal, 3 non-inverting terminal, right? We have different configurations about OPAMP. See, we have single-ended input, double-ended input. So there are many configurations as we can see. So see, here we have given input at non-inverting terminal, we have given input at inverting terminal. Now double-ended, we have just given the VD and connected by both the positive and negative terminals. So this is double-ended differential input. Similarly, we have double-ended output too. There are 2 outputs and 2 inputs. So we can say these are the double-ended output for the case of OPAMP. Here also we are having 2 outputs like this. Now coming to some common mode operation of the OPAMP. See what is common mode operation. The positive and negative terminals are connected with each other and resulting into common mode operation. So here see the 2 inputs are equally amplified. The 2 inputs are applied at the positive terminal 2 and the negative terminal 2, but listen carefully, this is not going to be shorted. Yeah, some students might make mistake like this, but it should not be there. Just understand that signal is applied at the negative terminal 2 and the positive terminal 2. That means at both the terminals, inverting and non-inverting, right? Here this is very important slide, and after that we will be talking about only concepts. So let us see the ideal operational amplifier in detail. So by up to this time we were discussing some common things about the OPAMP, the IC, the pin diagram of the OPAMP, right? But now this is the time that we should understand the ideal operational amplifier. Just listen carefully. I am talking about ideal operational amplifier. Okay, so ideal, what is ideal? So ideal operational amplifier where the open loop gain of the amplifier is infinite. What does it mean? How can a circuit having the gain to be infinite? So see, let us understand. So if I say any gain, let's say A, to be VO upon VI, right? Output voltage upon input voltage. This is the gain. This is the gain. Okay, gain of the circuit, gain of the OPAMP here, right? Now coming to this, if VO upon VI is my gain, Okay, then since if A is infinite, then it simply means that my Vi should be 0. Now, what is Vi? Vi here is V difference. Vi here is V difference. Just listen very carefully. What is the input voltage here? Input voltage here is the difference between the negative terminal as well as the voltage at the positive terminal. Here in this case, my difference voltage being V2 minus V1. At the positive terminal, I have given V2 voltage, and at the negative terminal, I have given V1 voltage. So my V difference is equal to V2 minus V1. That means if I write this VO here is V out for the operational amplifier, VO is equal to V out as mentioned in this figure, and this VI is equal to V difference. This is equal to V out upon, clearly I can write that V2 minus V1. This is my A. Right. So, if I want my amplifier to give gain to be infinite, then my V2 minus V1 must be 0. There should be no difference between the V2 minus V1. V out cannot be 0 because we are getting some voltage with high gain at the another end or another output terminal of the OPAMP. So it is very simple to understand that if this is tending to infinity, then this must tend to 0. If it is 0, then what does it mean? Then it simply means that these two terminals will always be at the same potential if I am taking or considering ideal OPAMP. This is first concept which is known as virtual ground concept of the OPAMP. Yes, what I want to say is just see from here we are deriving the virtual ground concept of the OPAMP circuit, right? V2 minus V1 to be 0. That means the terminals inverting and non-inverting both are at the same potential, and we will use this property. This property of virtual ground concept we are going to use for each numerical, for each derivation as far as my ideal OPAMP is considered. This is one. Okay, right? For ideal OPAMP, virtual ground concept is applied for every numerical, and here this is nothing but V2 minus V1, the difference voltage which has been given, which is being given to the two inputs of the OPAMP, that should be 0. This is one. Now next, this was one concept which I wanted to tell you. Now we are coming to the next concept. Yes, of course, for ideal operational amplifier. This just a second. So we have discussed about the virtual ground concept. Now quickly we are moving to the next concept. Here. Now for ideal OPAMP, this input impedance Zin, this input impedance is equal to infinite. Yeah. This input impedance Zin is equal to infinite for ideal operational amplifier. Okay. What does it mean? If this particular is infinite, that means this should be open circuit. Yes, and this is open circuit because because we are saying that op-amp is having very large gain, and for ideal op-amp the gain should be infinite, and the difference of the two input terminals is zero. Voltage difference between the input terminals is zero, and hence we can conclude that there is no resistance between the terminals, between the inverting and non-inverting terminals of the op-amp. That means Zin is infinite. The next property of ideal op-amp which we are going to discuss, that is Zout. Zout is low for operational amplifier. That I told that Zout is very low for operational amplifier. So what is Zout? Zout is output impedance. So Zout is output impedance, right? Now, these are three main consideration which we should learn, we should remember always while we are dealing with the op-amp circuits. Now here, this is equivalent circuit of the operational amplifier which clearly represent the Z input, Z out, and the difference voltage and the output voltage plus the DC supply given to the op-amp that to work, right? Now coming next. So op-amps has very high gain, that is one. Ideal op-amp is having infinite gain. See, ideal op-amp gain is infinite. For practical op-amp, gain is having some value. Okay. So this is the point which we should consider. For practical op-amp, the gain should have some value, and the ideal op-amp, the gain should be infinite. Now there are basically two configurations to work with op-amp. First is closed loop and second one is open loop. So open loop gain is when there is no feedback from input to output. That means there is no connection, no resistance between the output terminal and any of the input terminals, right? Then it is an open loop configuration, and in that case the gain can exceeds 10,000. Whereas in the closed loop operation there must be a feedback, and this feedback should be given at the negative terminal. This point has to be considered. So many applications are based on this closed loop negative feedback circuit, like your summer adder, which we will discuss later. So here closed loop configuration reduces the gain. Okay, it should have the feedback to be negative, to be given at the negative terminal or inverting terminal of the op-amp, and it is reducing the gain, but so many more characteristics of the op-amp can be improved by giving a negative feedback, right? Now coming to the inverting op-amp, right? Now, what we have learned up to this point, I am going to explain the concept of getting an output from any of the input terminal. Let us consider one OPAMP circuit which is known as inverting OPAMP circuit. Here, one OPAMP is there in the circuit. This is the OPAMP. This positive terminal has been grounded, right? The OPAMP which we are using is ideal OPAMP. There is one feedback, that is feedback resistance RF, which is connected to the input terminal of the OPAMP, directly to the negative terminal of the OPAMP, as we said that the feedback to be given at the negative terminal, and this feedback is given by the resistance RF, and this V1, okay, right, V1. This V1 terminal is inverting terminal. This voltage V1 is applied at the inverting terminal through this resistance R1. Simple. What we are going to find out is simply the output voltage. The output voltage, right? Now, first of all, I would like to revise the concepts which we have considered earlier. So, you need to check 3-4 points. First, at which terminal we have given the input. Number 1. Here in this case, we have given the input at the negative terminal of the OPAMP. Number 1. Second, there must be one RF. Check whether any feedback is given to the OPAMP or not. Number 2. Now third. Third is check what voltages have been applied at the terminals. Quickly, you will switch to the virtual ground concept in case of ideal OPAMP. Here we are considering ideal OPAMP, that's clear. So, first of all, you must see that positive terminal has been given 0 voltage because it is connected to the ground simply, right? If it is at 0 volts, it is at 0 voltage because it is connected to the ground. Now, using the ideal OPAMP property, I can say that this point must be at 0 volts. Why? Because my VID is 0 for virtual ground concept. If this point is 0, then there will be some current coming from the V1 input. So, this will go like this, and this is not going to flow here because this circuit is open. From ideal OPAMP properties, the circuit is open. No current is going inside the OPAMP. So, whatever the current be from the input terminal of the OPAMP for the input signal, input V1 from the applied voltage, then it will directly pass through the RF. That means if I say this I will go directly to this one, then it's not wrong because there is no current which is going to the OPAMP circuit or internal OPAMP circuit, right? So, this will directly go to the operational amplifier circuit. Now, what I will apply? I will apply KCL at this point. Kirchhoff current law. Okay. So, I will next consider the voltage and resistance, and then I will calculate the current. What is current in this circuit? 2 points. One is at V1 potential and second one is at 0. So just write, apply KCL, V1 minus 0 upon R1. This is my I, and this is same as 0 minus V0 upon RF. Okay. This will give me VO is equal to minus RF upon R1. This is my final formula, which is giving relationship between output voltage and input voltage. Input voltage is known V1. The feedback resistance is RF. The resistance through which the input has been applied, that is R1. So minus RF upon R1 into V1 is the output voltage at output terminal of the op-amp. This is the formula for inverting operational amplifier circuit, right? Now next, coming to the inverting op-amp gain. So this is same as with what we have derived, minus RF upon R1. And if I want, let's say I want this to be gain to be 1, that means I want output to be equal to input, then I will simply put RF should be equal to R1, and then I will get a gain of 1 for inverting op-amp. So we are having so many amplifier circuits like practical op-amp circuits, inverting amplifier, non-inverting amplifier, unity follower, summing amplifier, integrator and differentiator circuits. And in the similar way, we will be doing all the circuits one by one. Here we have discussed inverting amplifier circuit. In the next video lecture, we will be covering all these circuits for non-inverting, unity follower, summing, integrating and differentiating circuits. But two things which we want to, we should remember, that first is applying the virtual ground concept, and second is applying the Kirchhoff current law. So these two things to be in, always to be there with you when you are solving the numericals or anything else, right? So Jai Hind, thank you.